Hello chemists, this is Ms. Placino and you are watching Screencast 8.1 and Introduction to Nuclear Chemistry. Today we're going to start off with the fundamentals. We're going to address why nuclear decay occurs, and we're going to talk about the decay particles that are produced when a natural decay takes place. So let's start off with some basic terminology. When we're talking about nuclear chemistry, we're talking about the study of the atomic nucleus. Through most of our studies in chemistry, the nucleus kind of just gets ignored. A lot of the interesting chemistry happens because of the electrons. We know valence electrons are going to dictate the reactivity of an element. When those electrons are shared or transferred, we see bonds forming. And like I said before, the nucleus gets ignored. This unit focuses all on the nucleus. You can really just kind of again, for this unit only, disregard the electrons and not really worry about what they're doing. We're going to pay attention to the protons and neutrons that are in the nucleus. We're also going to address different nuclear reactions, both natural transmutations, we'll talk a little bit about those today, and some more specific reactions, fission and fusion. And we're also going to look at the products that are produced. You're going to hear the word radioisotope come up frequently throughout this unit. And when we say radioisotope, we're talking about an unstable isotope that is able to undergo radioactive decay, hence the name radioisotope. So we have a naturally occurring isotope that is just by its very nature unstable. And that instability is going to cause it to undergo radioactive decay. So you might be wondering, why does nuclear decay occur? Nuclear decay is natural. This is something that's happening all around you all of the time at really, really low levels. It's not just something like a nuclear power plant or a nuclear bomb. Nuclear chemistry is natural. There are some radioisotopes that are unstable. So when the nucleus is unstable, it's going to decay. We'll talk a little bit more about what that means, but you can think about decay as kind of the nucleus just trying to stabilize itself. You might be wondering, well, what causes a nucleus to be unstable? And a lot of that just has to do with the number of protons and neutrons that are present in the nucleus. So to interpret this graph a little bit, we've got number of protons or atomic number across the x-axis. We've got neutrons on the y-axis. This green line, I don't want to highlight it in red, represents the proton to neutron ratio of 1:1. So the number of protons equals the number of neutrons. Then you have that red curve kind of arcing upward. That's representative of stable nuclei. So it's not possible just to put any old combination of protons and neutrons together and end up with a nucleus that is stable. Sometimes people will call this the belt or the band of stability, kind of outlining it in red. And these are the ratios that are going to cause nuclei to be stable. If you fall outside of that ratio, you're going to end up with unstable nuclei. So they can sometimes be very unstable and they will rapidly decay, or they can be just a little unstable and they'll decay more slowly. But ultimately, every nucleus kind of wants, if you'll let me personify a nucleus, to get its proton to neutron ratio back in this band or belt of stability. So nuclear decay occurs as an attempt to improve the proton to neutron ratio. More often than not, we have too many protons or too many neutrons, and depending upon what the situation is in the nucleus is going to undergo a specific type of decay to address that issue. In your workbook, you have this page with a couple different types of decays. These are the 5 that I want you to be familiar with. And you can really just think about different decay modes as ways that a nucleus can try to attain a more stable configuration, try to get into a more optimum ratio of protons to neutrons. It's worth pointing out that all of these decays are what we call natural decays or natural transmutations. Sometimes you'll hear spontaneous transmutation or spontaneous decay. This means that you don't really need to do anything to get the nucleus to undergo something like alpha, beta, gamma, positron, or electron capture. This is something that just occurs naturally. Nothing needs to be done to push the nucleus to do it. Because the ratio of protons to neutrons is inherently unstable, you're going to get this decay to occur. So I'm not going to read this to you. You're more than capable of doing that. And on the next page, we have this table kind of summarizing what's happening with our different decay modes. So if you haven't done so already, why don't you pause the video, read over the page in your workbook where you've got information about the different decay modes, and we'll kind of walk through this table together to summarize. Okay, so these are the 4 things that I really would like you to know about these different types of natural decays. Again, so many different names: spontaneous transmutation, so on and so forth. I want you to know the symbol of the decay mode, and this can be found on your reference table, Table O. I want you to know what's happening inside the nucleus, essentially what change is taking place, be able to briefly explain why that type of decay is occurring, and then as that decay particle is emitted, its ability to penetrate the human body. So we're talking about basically high, medium, or low. Can it be stopped by your skin? Is it going to pass right through you? Can it kind of get a little bit through your skin? So on and so forth. All right, so first up we have alpha decay. The symbol for alpha is that. Sometimes you'll see alpha written as 42He because alpha particles really are a helium nucleus. Please don't make the confusion that a helium atom is an alpha particle. Those are not the same thing. An helium atom, in addition to the 2 protons and 2 neutrons, will also have 2 electrons. Alpha particles are only 2 protons plus 2 neutrons. So really what happens during alpha decay is the nucleus emits 2 protons and 2 neutrons. And hopefully the symbols, or my shorthand of P and N, make sense for protons and neutrons. This decay, this type of decay occurs because the nucleus is too big. A lot of times we see our really heavy elements or heavy atoms undergoing alpha decay. Lead is our last stable element. Once you get past lead, atomic number 82, all of those isotopes are inherently unstable, and many of them are going to experience alpha decay. Alpha particles have a very low ability to penetrate. They can be stopped by your skin. Please keep in mind that does not mean that alpha particles are not harmful. You can get alpha radiation burns on your skin, or if you ingest alpha particles for whatever reason, they're not going to be able to escape your body since they're going to be stopped by skin. So alpha particles, again, despite a very low ability to penetrate, they are very dangerous. All right, up next we have beta particles. Beta particles look a lot like electrons. In fact, they are electrons. So you'll see them represented using either of those symbols. Again, check Table O. Basically what happens is a neutron is turned into a proton, and an electron is emitted. And I've got all sorts of abbreviations and shorthands going on. Hopefully you can follow. And this occurs really because the proton to neutron ratio is unfavorable. More specifically, we have too many neutrons. And hopefully this makes sense. So we take a neutron and we turn it into a proton. We've lowered the total number of neutrons. We've happened to raise the number of protons, but we're starting to address that low proton to neutron ratio. Beta particles have a medium ability to penetrate. They can get through your skin, but they can penetrate to maybe a centimeter or so. They're going to get stopped by the tissue. Gamma radiation. That's a gamma. Sometimes you'll see it with 0, 0. Gamma radiation is just an emission of energy. Gamma radiation occurs because you can kind of think about it as just the nucleus is too energetic. And a lot of times gamma radiation is going to accompany something like alpha or beta radiation. So this is not going to make any real change to the identity of the nucleus. It's not going to turn into a different element. But this high energy, it's not even really a particle, it's just energy being emitted, has a very high ability to penetrate. You need something like lead or probably thick concrete will do the job at stopping gamma rays. They're even more dangerous than X-rays. They're extremely high energy radiation. All right, positron. It is kind of the opposite of a beta particle. Positrons are actually antimatter. You've got a beta particle, which is essentially an electron, so no mass and a charge of -1. A positron is the opposite. It has no mass as well, but it's got a charge of +1. Positron decay is the opposite of beta decay. In this case, we're going to have a proton turn into a neutron, and a positive charge is emitted. This occurs because there are too many protons. So now our proton to neutron ratio is too high. In other words, there are too many protons and not enough neutrons. So a proton can turn into a neutron, and it's going to emit a positive charge. Like the beta particle, positrons have a medium penetrating ability. I'll put a star next to those four. For something like Regents chemistry, those really are the ones to know, even more specifically alpha, beta, and gamma. I also like to talk about electron capture just because I think it's kind of cool. During electron capture, an electron is pulled into the nucleus. Might have wondered why this doesn't happen all the time. You've got all of your protons, a positive charge concentrated in one location, the nucleus, and then you've got these little tiny electrons orbiting around it. Why don't they ever get pulled in? Well, once in a while they do. We call this electron capture because the electron has essentially been captured by the nucleus. This occurs because we have too many protons. Hopefully that kind of makes sense. You have too many protons in the nucleus, so maybe the nucleus, you can think about it as being too strong or too attractive, and for that reason it's going to be able to suck an electron into it, and it's going to cause a proton to react with an electron. And when you combine a proton plus an electron, you end up with a neutron. The charges will cancel each other out. In this case, we're not going to see any emission particles, so we don't really have to worry about electron capture being able to penetrate. Okay, there are some practice problems as always. I would really encourage you to get familiar with alpha, beta, gamma, and positron decay. Know your ability to penetrate, and we're going to be building on this tomorrow. We're going to talk about actual decay equations and how to write them using our different decay modes. All right, thanks for tuning in. I hope you found this helpful.